Alcohols, phenols, ethers. This chapter we have already seen some preparation methods of alcohols, but some methods are still left that we will discuss now. And after that we will see some problems and also the physical properties and chemical properties of alcohols. Here we are starting from Grignard reagents as the starting material for the preparation of alcohols. Nucleophilic addition of Grignard reagent to aldehyde or ketone in presence of dry ether as solvent. This is the first step, followed by acid hydrolysis. Finally will give us alcohols. Fine. So Grignard reagent is basically organometallic reagent, that is carbon metal bond is present. So carbon metal bond when present, if you consider the polarity of this bond, metal is more electropositive. That means negative charge will be more compared to positive charge, and over metal it will be more positive charge that will be concentrated. So this C minus, it will behave as if it is a nucleophile. So see here we have taken this RMgX as the Grignard reagent, MgX this is the metal, and R it may be any new alkyl group or it may be phenyl also. So negative charge is present over this R group and it will act as nucleophile. So as if now this nucleophile is attacking the carbonyl carbon. So after that this attack, there will be negative charge generation over oxygen. So the positive part of Grignard reagent, that will be now attached to this negatively charged oxygen. So this is not the final product. Final step that we have to do to get the alcohol molecule as the product is acid hydrolysis. So here we will do hydrolysis under acidic condition, and OMgX, this part it will be converted to OH. So finally we are getting alcohol. Now if the starting material is formaldehyde, where both side of carbonyl group we have 2 hydrogen, fine, no alkyl group, so it will give us primary alcohol, and other aldehyde they will give secondary alcohol, because when we are saying that aldehyde, it is basically having formula RCOH, okay, and another R group that will come from the Grignard. So this part when it will be added here, this R group already there, another new R group is coming. That means now the carbon over which OH group is generated, it is containing 2 R group 1 H. That means it will be secondary alcohol. Fine. And if the starting material is ketone, there is no hydrogen, so final alcohol that will be tertiary alcohol. Fine. So now we will see this formaldehyde H2CO, and here after attack of RMgX we are getting this type of moiety, and then acid hydrolysis we are getting primary alcohol, because 2 hydrogen already there in the formaldehyde molecule, 1 R group is coming from Grignard reagent, so it is 1 degree alcohol. Then the second one is aldehyde, that is except formaldehyde, if you consider other aldehyde where the second H group is replaced by R group, now we will get 2 degree alcohol. And if it is carbonyl group, that means we do not have any hydrogen in the carbonyl. In this case 2 R group already there and the third new R group is coming. So ultimately here we have total 3 R groups, so it will be 3 degree alcohol. Okay. So in this way, starting from Grignard reagent and changing the other carbonyl compound depending on formaldehyde or other aldehyde or carbonyl, ketone carbonyl, you can make all the 3 types of alcohols, 1 degree, 2 degree as well as 3 degree. We will see a problem now which is based on Grignard reagent. Here we have a molecule which is basically acetone, CH3, COCH3. First it is treated with methyl magnesium bromide Grignard reagent, and in the second step H plus is mentioned, which is nothing but the second step. Remember, in the second step what we do? Acid hydrolysis. So here it is the same thing. Another starting material is CH3CHO, that means acetaldehyde. Same reagent, same condition, everything. So from the first case we are getting A as product, from the second one we are getting B as product. Now the question is asking, which of the following reagent can be used to differentiate between A and B? So if we want to answer this question, obviously first we have to understand the structure of A and B. A and B both are alcohol, that is fine. because this type of reaction we have just discussed. But what is the actual structure of alcohol, what is their that is 1 degree, 2 degree or 3 degree, depending on that we will understand what should be the reagent by which we can differentiate them. Now as it is ketone, so it will be 3 degree. This is aldehyde but not formaldehyde, so it will be 2 degree. Now 2 degree and 3 degree alcohol, how we can differentiate? Sorry, 2 degree and 3 degree alcohol we can differentiate by using Lucas reagent. Okay, so Lucas reagent, this reagent is used in Lucas test, basically Lucas test. So this reaction will be discussed later in this chapter, then you will be able to understand the exact mechanism what is here going on. But right now just remember, if we use this reagent, what will happen? The 3 degree alcohol, it will give positive taste very quickly, but it doesn't mean that 2 degree it will not give, but 2 degree can also give this taste, but it will take much time. Okay, so 2 degree alcohol which we get from the second one is having structure like this: CH3COH H, another CH3 is coming from CH3MgBr, fine, and A is this one, so this is A, this is B. Okay, 3 degree, 2 degree. Lucas reagent we can use to differentiate between these two, because 3 degree will give the positive observation for this test very quickly, but 2 degree, that will take some time. So depending on that we can understand that what will be the nature of this alcohol. Okay, here the other reagents, that is active metal sodium, that will react with both of these alcohol, because in both cases OH group is present, and FeCl3, that will also make complex with OH, so it will be common for both. K2Cr2O7, this is actually oxidizing agent, it can oxidize secondary alcohol and that will be converted to acetone again. But for tertiary alcohol, as there is no such hydrogen attached directly to carbon, so here oxidation is not possible by K2Cr2O7. But see, though here K2Cr2O7 at a first glance it seems that it can react with secondary but doesn't react with 3 degrees, so why not we can use this reagent to differentiate. But remember, whenever there is identification test, we choose this type of those type of reactions which can give us some immediate visual appearance or color change or some precipitate formation or some evolution of gas. But if that type of visual change is not there, we cannot use that test as identification test. So though K2Cr2O7 is behaving differently, but better reagent will be Lucas reagent. Second question: to synthesize 1 mole of 2-methyl propan 2-ol. 2-methyl propan 2-ol. Try to write the structure. Propan, that means it must contain 3 carbon, and 2 position there is OH group as well as there is methyl group. That means the structure will be like this. So if we want to synthesize 1 mole of this compound starting from ethyl ethanoate. Now ethyl ethanoate is basically ester molecule, right? So ethyl, that means Et, and this side, that is the acid part, that is also containing total 2 carbon. So the structure will be like this. Now it is asking how many equivalents of methyl magnesium bromide reagent will be required. So when Grignard reagent reacts with ester, basically first attack, it will remove this OET as leaving group. So there is no addition reaction, it is simple replacement of the OET part. So one CH3 group now will be attached, fine, and see in the final product there are total 3 methyl group. So 1 methyl group is already present in the ester starting material. Other 2 methyl group must be coming from CH3MgBr. That means we need 2 equivalent. So this is the actual reaction that is going on here. See, this is the OET part. So first OET will be removed. The first attack, it is not giving us any addition product. Second attack, now it is attacking at this position. There is formation of OMGBr, and then OMGBr in presence of acid hydrolysis, it will be converted to OH. So finally we are getting this molecule, which is Me3COH or 2-methyl propan-2-ol. So here answer will be 2 equivalent, 1, 2. So even without drawing all the structures, you can easily understand this one, but you have to draw the final product structure, that is 2-methyl propan-2-ol, because when you are drawing this, you will be able to understand how many methyl groups you need. One methyl group already present in the starting material, other 2 methyl group you have to get from methyl magnesium bromide. So that is why 2 equivalents of Grignard reagent will be required here. Okay, so this is an integer type of problem. Again, we are seeing some methods for preparation of alcohol, but here it is specially for methanol and ethanol, and it is manufacture of these 2 molecules, that is large scale preparation, okay, not laboratory method. So methanol large scale preparation is possible starting from water gas. Now what is water gas? It is a mixture of carbon monoxide and hydrogen, and this water gas is first prepared from coal. Coal is nothing but carbon, and temperature is very high, 1270 Kelvin. So this is water gas we are getting in this reaction. Now this water gas, if you are treating it with zinc oxide, Cr2O3 as catalyst, and finally you can obtain CH3OH, that is methanol. And if we want to get ethanol, there is a method which is fermentation method that is used for manufacture of ethanol. And remember, this process, that is ethanol formation by fermentation, it is only applicable for ethanol. You cannot make any other alcohol by this fermentation method. So what we do in this reaction, a glucose molecule splits into 2 pyruvate molecules before fermentation. So the first step is conversion of glucose molecule into 2 pyruvate molecules, and this is an exothermic process. So this exothermic process, it means some energy will be released, and that released energy is actually used to convert ADP to ATP, adenosine diphosphate to adenosine triphosphate. Triphosphate means 1 extra phosphate group extra. So from diphosphate, now we are getting another phosphate group attached. That is written here in this way, that is used to link inorganic phosphate. That means 1 new phosphate group you are attaching, and for that process energy is required, and that energy is coming from this exothermic process, glucose converted to 2 pyruvate molecules. So here glucose is converted to 2 pyruvate molecules. This is the pyruvate structure. We are calling it 8 because it is in CH3CO CO2 minus form. But suppose if there is H, no negative charge, then you can call it pyruvic acid. In this process, ADP is also converted to ATP. The next step is, now the pyruvates are broken down into 2 acetaldehyde molecule, CH3CHO 2 acetaldehyde molecule, and along with emission of carbon dioxide. Fine. So this is decarboxylation because carbon dioxide is removed. Then this acetaldehyde is converted finally into ethanol. Now see, acetaldehyde converted to ethanol, that means here H is added to this carbon and to this oxygen. So basically it is reduction, and this reduction is done by NADH, and NADH itself is converted to NAD+. That means it is oxidized to NAD+. So acetaldehyde is converted to ethanol utilizing this energy, and the hydrogen is coming from NADH. Fine. Now here the enzymes that are used, that is the conversion of pyruvate to acetaldehyde, where basically for this decarboxylation process, enzyme name is pyruvate decarboxylase. And see here, you can easily remember the name of the enzyme if you know what is your starting material and what process you are actually doing. This is decarboxylation, so the name is decarboxylase, and pyruvate because starting material is pyruvate ion. Second method is acetaldehyde now converted to ethanol. Now this is alcohol dehydrogenase. Alcohol dehydrogenase, that is actually the name of the enzyme. Now here the name is based on the product name because product is alcohol, and see dehydrogenase, that means It is related to the term dehydration, or sorry, dehydrogenation. Hydrogenation, dehydrogenation. Hydrogenation means what? Addition of hydrogen. Dehydrogenation is removal of hydrogen. So ethanol, if you remove hydrogen, you will get acetaldehyde. Okay, and vice versa. If you add, you will get ethanol from acetaldehyde. So that is why the name is like this. That is, the enzyme name is alcohol dehydrogenase. Fine. So this is the formation of ethanol by fermentation, and here the intermediates that are formed by acetaldehyde, and acetaldehyde is formed from pyruvate. Okay. Glycol. Now glycol is a special type of alcohol. What is so special about it? Because here 2OH group attached to two adjacent carbon. So this is the structure, CH2OH attached to another CH2OH. So this molecule is glycol, and there may be more than one carbon, but this is the simplest structure of diol that is possible. Okay. So glycol is any type of organic compound that belongs to the alcohol family but with two hydroxy group attached to different carbon atoms in the molecule. So here, and this point is also important, that different carbon atoms is carrying the OH, because if it is attached to same carbon, the name will be different. The name is in that case GM diol, this structure. But here two different carbon, two different OH attached. That is why it is the glycol. Now mostly the simplest member, that is the first member, that is known as glycol, but it is also the general term that you can use for any diol. Fine. Ethylene glycol, which is also known as, that is, if you want to apply the actual IUPAC name, it is 1,2-ethane diol, because here two carbon, so root word will be ethane, because it is alkane derivative. Ethane derivative, why I am saying ethane is CH3 attached to CH3. So if you remove two hydrogen from 2 CH3, it will be 1,2-ethane diol. That means it is ethane derivative, right? And it is a prominent member of the class of dihydroxy alcohols. That is, in general, if we say dihydroxy alcohol, this is the first member. You can also call it ethylene glycol, dihydric alcohol, or diol. How we can make it? Hydrolysis of ethylene oxide. Ethylene oxide is epoxide, this one. Fine. But first we will make epoxide. How we will make it? Epoxide can be made, or ethylene oxide, same thing, after catalytic oxidation of ethylene, that is this molecule C2H4. So what we are doing? We are using oxygen, that is oxidation. This is the catalyst. We are getting ethylene oxide. So this is the starting material for the preparation of glycol, and in presence of dilute acid, that means water is there, acid is there, we are getting ethylene glycol. So in this method, what happens? First the epoxide is protonated like this. Fine. And water then attacks to this epoxide, which is protonated, positively charged. Water will attack here. As a result, this bond will be broken, and finally you are getting two OH group at two different carbon. So this is the method for getting glycol by hydrolysis of ethylene oxide, and the ethylene oxide, which is the starting material, that you can get by oxidation of ethylene. Fine. Then another method for preparation of glycol, you can also use ethylene, and you can use a special oxidizing agent, which is KMnO4, because in the previous case also you have used oxidizing agent, but that is O2 in presence of Ag2O. But if you use cold alkaline KMnO4, then what happens? Here we are getting diol directly, and this reagent is also known as Bayer's reagent, and this reagent is basically used for identification of CC double bond, that is whether in the unknown compound, suppose you have any unknown compound, if you want to know whether unsaturation is present or not, then we use KMnO4 solution, because KMnO4 solution has a typical purple color, and when it is added to this, that is OH groups are added to across CC double bond, the purple color is discharged. So there is a visual change from which you can understand, yes, unsaturation is there. But this method is also can also be used for the preparation purpose of glycol. Now another method also you can use. From ethylene again that is same starting material, but now we are using HOCl. So when it is HOCl, basically you can consider this reagent as if it is a combination of HO and Cl. So HO part will be attached to one carbon, Cl part will be attached to another carbon. But this is not the final product we want. So what we have to do, this Cl we have to replace by OH. Then only it will be glycol. So for that purpose what we are doing, we are using aqueous NaCO3 sodium bicarbonate solution, and this Cl is removed in the form of NaCl, and we are getting OH, that is diol. This is the third method. Number fourth method for preparation of glycol, starting from ethylene dibromide. So it can also be prepared from ethylene dibromide, CH2Br, CH2Br, and in this case we are using aqueous solution of sodium carbonate. Fine. Here these two halogen BrBr that are removed in the form of NaBr, CO3 it is converted to CO2, and we are getting our desired molecule glycol. This is the fourth method. Number fifth method that you can use, starting from ethylene chlorohydrin. So see, ethylene chlorohydrin is nothing but this molecule that you have already seen, CH2OH, and which is attached to CH2Cl, and it is treated with milk of lime. Milk of lime is nothing but calcium hydroxide. So here also this Cl is now replaced by OH, and chlorine is removed in the form of calcium chloride. So this is the fifth method. So this is 2, 3, 4, this is 5, and if we see in the previous slide, you can consider this is the first method. Next, preparation of glycerol. Now try to understand the difference with glycol. In glycol, the molecule is up to this, but now this extra part is there. So now there are total 3 OH group attached to 3 carbon, and all these 3 carbons are different. This molecule is also very important because it occurs naturally in many natural fats, and it is also found in long chain fatty acid in the form of glycerol ester, because it is after all alcohol, right? And alcohol is one of the part of ester. So here you can basically use 3 individual carboxylic acid to make 3 ester linkage. So it can also remain in the fatty acid chain in glyceryl ester form, which is also known as triglycerides, because it is forming total 3 ester linkage. And the alkaline hydrolysis of these fats, that is the ester that we have, triglyceride, if we do alkaline hydrolysis, that is ester hydrolysis, then we can get back the alcohol. In this case it is glycerol, that is the alcohol, and the reaction is known as, which is very famous term used, saponification. Fine, which is nothing but ester hydrolysis, but not any kind of ester, it is triglyceride. So see, here we have the example. Here we have this CH2, then OCOR. So this is one ester linkage. Now the middle carbon, another ester linkage. This is third ester linkage. So here all the R groups mentioned as different R group. Okay. So the first one is simple R, then R prime, then R double prime, and we are using 3 moles of NaOH for 1 mole of triglyceride, because ultimately we have to break 3 ester linkage, right? 3 moles of caustic soda or NaOH, and finally this part will be broken and there will be formation of glycerine or glycerol. Okay, and the 3 carboxylic acid part we will get. So this is sodium salt of RCO2H, sodium salt of R prime CO2H, sodium salt of R double prime CO2H. Okay, it is also known as metal soap because it is sodium salt form. If you acidify it, it will be converted to the acid form. So this is the general expression. Now take actual example. See what kind of molecule we have taken here. OCO, then the R group is CH214CH3. So this is a long chain. This is also same group, this is also same group. So all these are, suppose it is simply R. So all the R groups are same. Then we are getting glycerol or glycerine and sodium salt of this chain, which is basically known as palmitic acid. So palmitic acid, if you are removing the hydrogen of carboxylic acid, and if there is sodium ion, it will be sodium salt of palmitic acid, or you can call it sodium palmitate. Fine. So this is the example of saponification, which is also the method for preparation of glycerol. Now after preparation method, next we will see physical properties of alcohols. Now alcohols, it consists of basically two parts. That is, if you think at it as if it is a derivative of alkane. So suppose we have alkane CH3CH3. If you remove simply one hydrogen with OH, you will get ethanol. Fine. So there is alkyl group present, which is because it is a derivative of alkane, and also there is hydroxyl group. So from this alkane we are getting CH3CH2OH. So there is alkyl group present, there is OH group present. Now the properties of alcohols, it is chiefly because of this hydroxyl group, and this is the group which is bringing some different characteristic to this molecule, because if it is alkane, you do not have any polar group like OH, the properties are completely different. But as when you are replacing just one hydrogen with OH, all the properties will be changed. So the properties of alcohols, it is because of chiefly hydroxyl group, and the nature of alkyl groups simply modify these properties. It is not that alkyl groups, they will not have any effect. Obviously they will have effect, but it is simple modification. Main properties because of OH. But suppose if this alkyl group, if it is very long chain or very short chain, or there may be some branching, or it may be simple chain, so different possibilities are there, and all these differences or variety in the chain, that will also modify the properties of OH group. Here the lower alcohols, if we consider, lower alcohol means suppose CH3OH, then CH3CH2OH, that is the first members. Then they are liquid at room temperature. Under normal condition they are in liquid state. And alcohols containing 4 to 12, that is up to 3, that is methanol, ethanol, propanol, 3 carbon maximum. These 3 are alcohol. Now when you are entering from 3 to 4 and then 5, 6, 7, 8 up to 12 carbon atoms when present, they are somewhat viscous in nature or oily. So it is still liquid, but the liquid nature, it is now becoming more viscous, more dense, more oily. And if you further move, that is after 12, now it will gradually, there will be change in appearance, it will become waxy solid. Okay. So in this way, as the number of carbon atoms are increasing, the physical appearance, that is also changing. So see, here OH group is fixed, you are just changing the alkyl group. And what change you are doing? You are just simply increasing the number of carbon atoms, and there is change in the physical appearance. Alcohols are colorless, there is no specific color. They generally give a sweet smell except for glycerol and a few lower alcohols. They are flammable and produce a blue flame. The first property that we will discuss is acidity of alcohols. Though this is not exactly physical properties, some chemical, it is mainly because of these properties, some chemical reactions are also we can observe for alcohols, but we are discussing this under physical property. Acidity of alcohols, it is mainly because of this proton that is attached to the OH group, but it is not very strong acid, it is very weak acid. But as they are very weak acid, so active metals, they can replace this H. So OH group can be converted to ONA, OK, etc. That means now it is converted to alkoxide. Alkoxide means, suppose you have ROH, but now in presence of metal, it is converted to RONA. So this is basically RO minus Na plus. So this is known as alkoxide. So if it is R group is Me, it is methoxide. R group is ethyl, it is ethoxide or propoxide. Okay. Primary alcohols are generally more acidic. Primary alcohols, we know what is, that is the carbon with which OH is attached, that is attached to only one carbon. So these type of alcohols are more acidic than secondary. Secondary alcohols are more acidic than tertiary. Now why it is so? Because as you move from primary to secondary to tertiary, the electron donating group attached to the alkyl group is increasing, and that electron donating effect is increasing the electron density. So when it is simple one R group attached to the carbon which is containing OH group, it is 1 degree and there is plus I effect only from one R group. But suppose another hydrogen, if you are replacing with another R group, so plus I effect is also increasing. Sorry, it is OH. So that is the reason why when you are moving from 1 degree, 2 degree, 3 degree, why the acidic property is increasing. Now here we have a picture. See, this is in this picture you have different types of alcohol. See, CF3CH2OH, then methanol, ethanol, Me2CHOH, isopropanol, Me3COH, tertiary butanol. Okay, and pK values are gradually increasing as you are moving from left hand side to right hand side. So see, if this is the scale of pK, the red vertical line that you are seeing, that is actually the position for pK of water. That means all these three lines that you are seeing that are below this, that is the value are lesser than the pK value of water. Now higher is the pK, that is when pK is increasing, that means acidity decreasing. So these two are inversely related. Now what is pK? It is the negative logarithm of Ka value, and Ka is dissociation constant, that is when any acid is dissociating. Suppose you have acid HA, it is dissociating H plus and the conjugate acid is A minus. So dissociation constant, that will be concentration of H plus A minus divided by concentration of unreacted HA. So higher is the value of Ka, higher will be the acidity. But when it is pK, it is negative logarithm of Ka. So now the relationship with acidity, it will be in reverse. That means as you are moving towards left hand side, pK is decreasing, acidity is increasing. Now here see, compared to methanol, when we have CF3 group, that is one hydrogen, if we replace by CF3 group, this is electron withdrawing, so it will increase the acidity of hydrogen. Okay. Similarly, though phenol we have not yet discussed, because that is a special type of alcohol, because OH group is now attached to phenyl group. But see, here pK of phenol, that is further less, even lesser than CF3CH2OH. So why so special? It is so acidic in case of phenol, because in case of phenol, the H, if we remove, the conjugate base is phenoxide ion, which is highly stabilized because it can take part in resonance with the double bonds of benzene ring. So that is why it is so acidic in nature. And as we are moving towards this side, see water pK. Suppose if you consider this point, all the lines that you are seeing in the right hand side, they will be less acidic than water, and all the lines that are in the right hand side, they will be more acidic than water. Fine. And here number of alkyl groups are increasing, so this H, it will have now less and less acidity. Fine. The second property that we will see, solubility of alcohols. The hydroxyl group that is present in alcohol, it can take part in intermolecular hydrogen bonding. So suppose here we have C ROH, which is the alcohol. Right. Now this can make intermolecular hydrogen bonding, which makes alcohol soluble in water. Now these are water molecules. See the purple color molecule, this is water molecule, and the green color molecule, that is alcohol. So you can extend this both sides. So here hydrogen bonding is possible not just between two alcohol group molecule, but hydrogen bonding is also possible between one alcohol molecule and the water molecule. Okay. Now this C, this oxygen is taking part in hydrogen bond formation with the H of one alcohol, and the hydrogen of water, that is also taking part with the oxygen of another alcohol. So in this way a chain can be formed. So because of this type of interaction, now alcohols are soluble in water. Fine. However, the alkyl groups that are attached to the hydroxyl group, they are hydrophobic in nature, because the alkyl group is nothing but consists of carbon and hydrogen. It is hydrocarbon, so it will be hydrophobic in nature because it has any affection for water. It is non-polar, it has no affection for polar water, so it is hydrophobic in nature. Okay, the solubility of alcohol decreases with increase in the size of alkyl group. So as it is hydrophobic in nature, it has phobia for water. Hydro, the word is related to water. So as it has no interest for water, so obviously when you are increasing the alkyl group, size of alkyl group is increasing, that is you are increasing carbon, and when carbon is increasing, obviously hydrogen will also increase. So in that case, solubility will decrease. So keeping the OH group fixed, if you are simply increasing the alkyl group size, solubility decreases. And here we can see that solubility in water unit is gram per 100 gram. Okay, so all the values that you are seeing, these are the amount of alcohol in gram, that is 2.7, that means 2.7 gram of that particular alcohol you have dissolved in 100 gram. So that is the solubility possible, not more than that. Now the first three compound, that is methanol, ethanol, propanol, the first three member, they are infinitely soluble because now the alkyl group size is not so large. But once you have entered 4 carbon, then 5 carbon, then 6 carbon, gradually the size is becoming large and large and solubility is decreasing. And once you have reached this, where 10 carbon is present, decanol, it is insoluble in water. Fine. So in this way, with increase in number of carbon atoms, keeping OH group intact, because if you are increasing OH group, you are also increasing alkyl group, then you will not get proper explanation for it. You have to keep one position fixed. So keeping OH fixed, that is just one OH. When you are just increasing the alkyl part, solubility decreases. And alcohols with more than 2 OH group, if it is present, suppose now you have kept the alkyl part fixed and you are only increasing the number of OH group, then what will happen? It will make it more soluble than similar alcohols where only one OH group is present. So number of OH group when increase, solubility increases, and when the size of alkyl group increases, solubility decreases. Okay. So here we have this graph where in the y-axis we have solubility in water at 25 degrees centigrade. Unit is gram per 100 ml of water. So when you are increasing number of carbon atoms up to 3, it is completely soluble. So see, now the solubility, it is very high and there is a double line. It means that there is a drastic scale change. So here the value is very high, it is infinitely soluble. So it is so high value, you cannot keep it in the same graph. So that is why we have given some gap. So there is a gap. So suppose after 8 there is some very high value. So it is completely soluble. But once you are jumping from 3 to 4, there is a drastic decrease. Okay. So now the values are very less. See, it is for butanol, it is around 9. Then for pentanol, it is around 2.7. Okay, this value. So this will be the nature of graph. Now why we are discussing nature of graph? Because sometimes if question is given with some graphs, that is the solubility of alcohols present in y-axis, in the x-axis number of carbon atoms are increasing. Suppose different graphs are given in option 1, 2, 3, 4 and you have to choose which graph is giving you the proper change in solubility with number of carbon atoms, then you can easily choose what option will be the correct option. Okay, so that is why the graph nature also we should understand properly. Fine. Now the third physical property that we will see, boiling point. Now boiling point increases with increase in number of carbon atoms. Now it is very simple to understand, because when you are increasing the number of carbon atoms, mass is increasing, and when mass is increasing, van der Waals forces also increases. So that is why boiling point directly increases. Here in this picture you can see, here we have given some gap, because if it is 0, there is a gap, because see, this difference is 40, but 0 to that is, sorry, I am trying to say, if this is 40, there is a, this gap is actually very high. Fine. So to that is scale jump is there. So to denote that, sometimes this type of double line is given. And number of carbon atoms in the x-axis. All are liquids at 25 degrees centigrade. Fine. So we have taken these alcohols that are liquids at 25 degrees centigrade. Though it is true that, remember, the physical appearance, how it changes, up to 3 it is simple liquid, but when it is 4 to 12 it is liquid, but it is very viscous liquid, but still it is liquid. So now we have here up to 10 number of carbon atoms, and boiling point, it is smoothly increasing. Fine. The boiling point decreases with increase of branching in the carbon chain. Now suppose you have same number of carbon atoms, you are not increasing carbon atoms, keeping the carbon atom number same. If you are changing the branching, so in one cases it is simple chain, simple long chain linear, in some cases there is branching. So what will happen when you are increasing the branching in carbon chain, then also boiling point decreases. Now it is decreases. Fine. Now the reason is when we are increasing the branching, there is decrease in surface area. So suppose it is a linear chain and then wedge group, but suppose there is a branching like this and then wedge group. Now it is more spherical, right? So when it becomes more spherical, we know surface area it will decrease, and when surface area is decreasing, van der Waals forces also proportionally decreases. So that is the reason now boiling point that will decrease, because when van der Waals force is decreasing, that means you don't have to overcome much the van der Waals force, you don't have to put much energy, that means boiling point is less. That is, to convert it from liquid state to vapor state, you don't have to apply so much energy, because van der Waals force is weak. Among isomeric alcohols, primary alcohols have higher boiling point and tertiary alcohols have lower boiling point. So this is the result of this second point, right? Because suppose if you have primary alcohol from 4 carbon chain alcohol, so this is linear chain, but there may be branching also possible like this. This is also 4 carbon, but branching is there, so it will have lesser boiling point. So primary alcohols are having higher boiling points. Okay, though here both are actually primary. So basically, if the branching, if you are having here, now it is 2 degree. Okay, so this is 1 degree, this is 2 degree, so 2 degree will be having lesser boiling point. So isomeric alcohol, because you have to keep the carbon number same, that is why isomeric. Formula is same, only branching is changing. They have higher boiling point than the corresponding other organic compounds also, such as alkane, aldehyde, ether. Okay, we'll come to that point later. First see here this picture, we have different methanol molecule, CH2OH, one methanol, another CH2OH, then CH2OH. So different CH2OH is there. Okay, and there are some interaction present, as hydrogen bond is possible between 2 methanol molecule, that is 2 alcohol molecule, and this is the non-polar part. Okay, so non-polar part also, it can have some interaction with the non-polar part of the other alcohol molecule, which is van der Waals interaction, because it has nothing to do with polarity. Okay, wedge group, there is already some polarity generated, so dipole-dipole interaction is possible. But suppose if you consider the non-polar part, the non-polar part where polarity is not generated, in that case you have to consider van der Waals force. So in the non-polar part, what happens, suppose if any part is non-polar, but at a particular time there is instantaneous dipole generation. So as it is non-polar, all the electrons and positive charge and negative charge, they will be distributed properly. But suppose at a particular time, if negative charges are accumulated at one place, positive charges accumulated at the other region, then what will happen? Some dipole will be created. So if these two dipoles are there, suppose this is negative side, this is positive, this is positive negative, so there is interaction possible. So this is van der Waals interaction. Okay, so this is possible between 2 alkyl group. So that is the reason when you are increasing alkyl group, then that is you are increasing number of carbon atoms, then also van der Waals interaction increases. So to break all these van der Waals interaction, you have to put more energy. And the last point, it is saying that if you compare boiling point with alkane, aldehyde, ether, that is which are having more or less same structure. So suppose you have this 2 carbon OH and you have 2 carbon ether. So these two are having same, I mean closure molar mass, formulas are almost same. So when you are having this type of almost similar molar mass but different groups are present, that is alkane, simple carbon and hydrogen, then aldehyde, CHO group present, then ether, COC linkage present. So compared to all these different types of compounds, in case of alcohols always boiling point will be high, and it is because of the presence of intermolecular hydrogen bonding that you can see here. All these green dotted line, that is indicating the hydrogen bonding. Fine. Chemical properties of alcohols. Alcohols exhibit wide range of spontaneous chemical reactions, and this reaction is possible because of two type of cleavage. Because our alcohol is ROH, so there is carbon oxygen bond, there is also OH bond, this one. So cleavage may be at CO bond or it may be at OH bond. So when the bond between carbon and oxygen is broken, then alcohols, they react as electrophiles. Okay, and when the bond between oxygen and hydrogen is breaking, they are acting as nucleophile. Now the reason is when OH bond is broken, you are getting RO minus type of species which is carrying some negative charge. But when CO bond is broken, that means when OH is removed, there will be positive charge. So now it will behave as electrophile. Okay, so this is the basis of their why they are showing chemical property, different chemical properties. So first we will see all those reactions that are because of the cleavage of carbon oxygen bond. That means now it will behave as electrophile. And under this category A, the first reaction that we are going to see, reaction with hydrogen halide, that is HX. It may be HCl, HBr like this. Another reagent possible, SOCl2 thionyl chloride, or it may be PCl5, PCl3. So reaction with of alcohol with all these reagents. Basically when we treat ROH with all these reagents, what you get? You get RCl. That means you are getting alkyl halide from alcohol. So alkyl halide formation from an alcohol, and this part you can also get detailed explanation in the chapter haloalkane and haloarine, when we have discussed the synthesis methods of alkyl halide starting from alcohol. Then there also you can find the detailed discussion. Alkyl halide formation from an alcohol and a hydrogen halide affords an important example of a reaction where the CO bond of the alcohol is broken. Okay, so this is the reference you can take the help of. So first what happens, ROH in presence of HX, this OH, it may be protonated, it will be removed, there will be R plus formation. Detailed mechanism you will find it here, preparation method of haloalkanes. So the net change is ROH is OH is replaced by X. So this is substitution reaction. Okay, so see here we have taken HBr as HX, OH is removed, Br we are getting. So mechanism of this displacement, it may be either SN1 or it may be SN2, depending on the structure of the alcohol, that is what type of alcohol you have taken, both the mechanism possible. Again I am saying detailed mechanism you will find it here. Now if it is SN1, the first step is slow step and it is the formation of carbocation R plus. Here OH is protonated by taking H from the acid is HX, and this carbocation now it is attacked by the negative part of the reagent which is Br minus. So this is SN1. Second step is fast. It is involving two steps, step 1, step 2. but SN2 is single step. So in single step, here the bond breaking between R and O and the bond formation between R and Br both are happening simultaneously. So that is why it is single step. Okay, product is same. Now use of HX we have seen. Now what about the other reagents? Thionyl chloride. Thionyl chloride is also useful for preparation of alkyl chloride, especially now see it is not alkyl, we have not written alkyl halide, it is alkyl chloride because you are using SOCl2, so obviously the halogen is Cl, it is not alkyl bromide or iodide. So the alkyl chlorides that you are getting, especially when the use of strongly acidic reagents, is undesirable. So in the previous method what you are using HX, that is HCl HBr, but suppose your substrate it is having some sensitive area where acidic environment is not suitable. In that case what you will do? You want to avoid strongly acidic reagents, so you can use SOCl2. Fine. Addition of 1 mole of alcohol to 1 mole of SOCl2 gives an unstable alkyl chlorosulfide first. So this is the structure of alkyl chlorosulfide. Lone pair of oxygen attacking sulfur, one of the Cl is removed along with this H. So that is why it is written minus HCl, and you are getting alkyl chlorosulfide. Finally what will happen? This part will removed in the form of SO2 and you are getting RCl. So this alkyl chlorosulfide decompose on mild heating to yield the alkyl chloride and SO2. Other halides that are useful in converting alcohols to alkyl halides, you can use PCl5, PCl3 if you want to convert ROH to RCl. You can use PBr3 for conversion of ROH to RBr. You can use Pi3 for conversion of ROH to RI. Okay. Here the mechanism is given for SOCl2. So this bond is broken. SO double bond is formed. So we are getting R plus carbocation. SO2 will be evolved, Cl minus. Now this Cl minus it can attack. Fine. Now here another mechanism is also there, that is if this RO bond is broken, there is negative charge over oxygen. Now carbocation is also there. Now this negative charge, if it is making double bond between sulfur and oxygen, again Cl is removed. So this is another possibility. So ROH, this picture basically I have also added in haloalkane halo adding chapter. The reagent HCl along with catalyst anhydrous ZnCl2, which is basically the Lucas reagent. Remember the problem that we have discussed in today's class. So here HCl along with this catalyst is actually required if alcohol is 1 degree or 2 degree, but for 3 degree simple HCl is fine. So it is giving us RCl. This is also known as Group's process. Then you can generate in the medium HBr by using NaBr H2SO4. So it will generate HBr. This is another reagent you can use for conversion of OH to Br. Then PX3, that is PCl3 or PBr3, PCl5 and pyridine SOCl2. So this is the method of SOCl2 we have seen discussed first. And here pyridine is also used sometimes. Why? Because here the HCl that is removed. See, this is HCl removed. So this HCl will be consumed by pyridine. So this is the byproduct. So if byproduct is consumed by pyridine, what will happen? Equilibrium that will be shifted easily from left hand side to right hand side. Fine. And okay, so these are the methods if you want to convert alcohols to alkyl halide. Different types of reagents are there depending on the requirement. If that is whether the alcohol is 1 degree, 2 degree, 3 degree, depending on that you may vary the reagent. If you want to avoid strong acidic reagent, then you can use SOCl2. So these are the different variety of reagent that we can use. What is the final product? That is the major product, because there may be more than one product. A in the given reaction. So given reaction, here we have OH group. Now see, this is 2 degree alcohol. We are using reagent HCl and we have to find out major product. Now if you look at the options, option 1 and option 4, this is substitution reaction product. But option 2 and 3, this is elimination, right? But when it is HCl, basically we will get substitution. So first, in presence of H plus, OH will be protonated. It is a good leaving group, so it will be removed. Now there is positive charge, and this positive charge is 2 degree. Now you have to be very careful in this stage, that is there any rearrangement possible by which you can generate more stable carbocation? So just check it, because if it is possible, the product will be, major product will be only that product which is you are getting only after rearrangement. So here if this hydrogen is shifted, that is hydride shift, it is known as 1,2 hydride shift because the position is 1 and 2. 1,2 hydride shift is occurring and you are getting a new positive charge here which is 3 degree, and it is more stable, and that is the driving force for rearrangement. Now finally Cl minus is attacking here. So this is substitution, so you can easily cancel out these two. But if it is direct replacement of OH by Cl, this is actually the product, right? But that is not the case. The final product, it is rearranged product. And it is matching with option, so it is matching with option 1, right? So this is the correct option. Fine. Here the next methods, that is still we are continuing chemical properties of alcohols. Only one property we have seen, that is reaction with hydrogen halide or SOCl2, PCl3 or PCl5. Okay. So this is the first method we have seen, and under this category different reagents that we can use, we have also seen that. We have discussed one problem. The next method that I am going to discuss in the next class, because it will take much time, that is dehydration. So this will be second chemical property. Okay, so we are ending the session here. Thank you for listening.